He's earned his PhD degree from Vellore Institute of Technology, India, and his MTech from Bihar Institute of Technology. He's also published more than 21 research articles in SCA and Scopus indexed peer-reviewed journals, presented papers in 20 plus conference proceeding, authored one book chapter, and holds 3 design patents. So, which in such a with such a diverse background, combining academic research, we are inviting to this session, sir.
Thank you, sir. Thank you, Vinod, sir. I am audible?
Yes, sir. You are audible, sir.
Sir, my screen is visible, sir. Vinod, sir. Okay, thank you. Can I start, Vinod, sir, or should we wait?
Sir, you can start, sir. You can start.
Okay. Okay. First of all, I would like to warmly welcome all the participants and organizer. I sincerely thank Mr. Vinod, sir, Assistant Professor, and Dr. E. Sivakumar, Professor and Head, Department of Mechanical Engineering, for organizing this FDP and for giving me the opportunity to present here today. So myself, Dr. Sourabh Soni, currently I am serving as a postdoctoral research associate in Kongju University, and today I am talking on the composites, additive manufacturing, high entropy alloy, and material characterizations. So before proceeding into the main content, being as a faculty in engineering college for around 11 years, I can relate the significance of this FDP for especially for young faculties who are new in this field. So why this FDP means these FDPs are conducted to improve the teaching approaches and fostering research, innovation, and entrepreneurship among the faculty members. And these are the some bits. These are the some key objectives like upskilling faculties in emerging area. So with the help of my presentation, I can try to upskill faculty members in my field, which is basically totally material processing and characterization. Enhancing teaching methodology. Somehow I used some innovative tools so that they can realize what are the teaching methodology techniques. Research and innovation. So what is the research trend is going on the current field? They can relate and they can progress with it. National development. I will suggest some tools, technique, and processes which can help our faculty members. Entrepreneurship. Somehow, if they are able to transform this technology into the product, so they can enhance the entrepreneurship also. Strengthening institutional leadership. I think Mr. Vinod sir and HOD sir did very well by conducting this type of FDP. Promoting well-being. Okay, if our students will be more skillful, then it will be more beneficial for our well-being. technology for educations. Okay, from this kind of FDPs, we can train our teachers what kind of technology and evolution is going on. And collaboration, another thing is collaboration. So from this PPT or this slide particular, I want to highlight that why we are discussing research today. So first thing,
sorry to interrupt you, sir. We can't able to see your slides, sir.
Oh, sorry. Sir, I shared. Is not visible?
Yes, sir, it's not visible to us, sir.
Wait. Now visible, sir?
No, sir. Now it's okay, sir.
Now visible?
Yes, sir. Yes, sir. Now it's okay, sir.
Now it's okay? Okay.
Yes, sir.
Sorry, Vinod, sir, and sorry, participants.
Sir, so, no issues, sir.
Okay. So again, I will just go through it. So as a faculty member in engineering college, I can relate this kind of FDP for our young faculty members. So why we are discussing research today? As a personally, I observe that these Korean graduate students are more skillful because of technology evolution. So we need to equip our students also with this kind of technology evolution, so that they can compete with the other international competition or in research activity especially. So for that, my suggestion, not my suggestion, I observed in the foreign, professors are forming the research group and centers, and in that center and group, so many BTech students, master students, and PhD students are working, and further they are collaborating with academia and industry regarding their research work, and also participating, and professors also encouraging students for training, internship, and research position. And further, as a cumulative approach, they are exploring the funding opportunities for their research. So these are the trends usually in foreign countries are going on. So we means, as an Indian postdoctoral associate, I also want to explore this area for our faculty members. So now comes to the topic. So today we are talking about the composites, additive manufacturing, high entropy alloy, and material characterization. So first topic is the composites. So if anyone asks what is the composite, so first thing comes in the mind, what is the difference between alloy and composites? So basically from this slide you can see this is the alloy. So in alloy, basically atomic level mixing is there. But in composites, if you use two or more distinct species like metal, ceramic, polymer, so they remain separated at the microscopic scale, but they will do their work with the presence in their base material. So this is the main difference between the alloy and composites. And if we want to classify the composites, what are the composites are available in the materials arena? So there are basically two kinds of composite. First one is based on the matrix, and second one is based on reinforcing material. So based on the matrix, the populars are the metal matrix composites, polymer matrix composite, and ceramic matrix composite. And if we look for the application, specifically application, then structural composite and the particulate composite are the more popular among the other composites. And if we had word composites in some FDP or some presentation, so what is our perception? It is more useful than the conventional material, maybe more lightweight and more strength. Wait 1 second. From this diagram, I want to highlight this. If we heard the voice of composite or term composite, we can relate that this has a very low weight as compared to conventional material and having more strength than the composite material. That perception is totally wrong. The strength the lightweight of the composite is totally dependent upon the what kind of matrix we are using, what kind of reinforcement we are using, and which processing route we are following to fabricate the composite. So these three major factors is governing the total overall result of the properties of the composites. And these are the some application of the composite. Automobile, huge application in automobile field. Industry 4.0 is now we are using fiber composite, polymer composite, aluminum composite in industry 4.0. Electronic semiconductor also, as in our previous session, Dr. Mohan sir told that carbon nanotube composite is using in the thermal industry. So of course, electronic and semiconductor field also using the composites. Defense and medical hugely used because Kevlar fiber and other carbon fiber, glass fiber we are using in aerospace and aircraft. Here I would like to highlight. And these are the some mechanical parts, module and tools in which field we are using the composites. So there is a huge demand of composite in this material science industry, and we are using also, and this field is under evolution also. In future 10 or 20 years, definitely this composite will replace the conventional materials. So from this slide, I would like to highlight which kind of matrix materials are available in the composite arena. So if you follow the metals, so aluminum, copper, magnesium, titanium, like this kind of matrix material. If you go for the polymer, then epoxy is the most popular and widely used. If you go for the thermoplastic polymers, then these are the some matrix material available. If you are looking for the fiber, then glass fiber and carbon fiber are in the forefront, and follow with after the carbon and glass, some aramide and boron fiber is also very popular. And in the research kind of activity, we are following the jute fiber, bamboo fiber, and cotton fiber for producing the composites. And what about the reinforcement material? Huge variety of reinforcement material. What kind of property you want to increase in the basic matrix material? So based on that, we can use the reinforcement material. So there are two kinds of reinforcement material: micro size and narrow size. So micro size means their size is in the range of micro, and nano means nano size. So they are usually categorized, and further they are categorized in carbon nanomaterial. Some are in the ceramic nanomaterial, ceramic carbon nanomaterial. So there is a huge variety. So if we are talking about the composite, so these 5 words are more popular. First one is the composites. Composites, like nowadays we are using composite as a conventional material. So composite means normal composite. We are not emphasizing in anything in the composite. If nano composite means in composite we are using the nano size. We are adding the nano size reinforcement. If we are talking about the hybrid composite, means we are using more than one reinforcement in the matrix material to fabricate the hybrid composite. If hybrid nano composite means we can use the more than one filler, in which one is compulsory is the nano size. So in that composite, we are calling it is as a hybrid nano composite. And apart from these 4, one more field is trending: functionally graded materials. So in which functionally graded material we are using the graded distribution to achieve the directional property. So this is also one of the emerging field after the composites. So you can read. So in previous sessions by our speakers, I observed that they introduced the composites. So I skipped that composite part. So now I am talking about the metal matrix hybrid composite, composite and nano composites. So as from this diagram you can see, there is a huge number of publication is going from since 2010 to 2024. 2025 is going on, so still there are some less. Definitely it will cross 24 in next 4-5 months. So huge publication in hybrid composite and nano composites. And for fabrication, this composite, some fabric processing routes also they are using, and among them, stir casting is the widely used. Stir casting is the liquid processing route, and powder metallurgy is the solid processing route. So in liquid processing condition, stir casting is the widely used, and solid state powder metallurgy is widely used. And apart from these two technique, spark plasma sintering. Spark plasma SPS, we are saying that SPS is also popular to produce specimen, and this comes under the solid processing route. So these three are the major contribution, having the major contribution. Apart from these three, liquid and solid, additive manufacturing is also now trending. So in additive manufacturing, I personally observed that DD, especially DD and SLM are researchers are using to fabricate hybrid nanocomposites. Apart from that processing, there are some main aspects like challenges in fabrication. What kind of challenges in fabrication we are observing, and what are the fabrication technique we can use to fabricate that composite, and what are the strengthening mechanism involved in the property enhancement, and what are the future opportunities we need to explore by the upcoming researcher. So this diagram showing this all four aspects, you can observe this. And further, if you want to improve the property of hybrid composite, so this is the actually I want to show the tensile specimen, but in hurry I prepared like this. So if we observe the agglomeration, definitely we will enhance the brittleness of within the specimen. So we need to achieve the uniform dispersion within the composite specimen, so we will get the improved mechanical property. And these are the some most relevant strengthening mechanism generally involved in the MMHC, means hybrid metal matrix hybrid composite. And this is rarely, means very rarely this mechanism is activated, but contributed more as compared to the most relevant. So before going to the processing condition, I want to highlight that the dispersion of reinforcement is the very important, very critically important. So for achieving uniform dispersion, various kind of dispersion techniques are available in the material science field. So first one is the ultrasonication. In ultrasonication, what we are doing, we are pouring our reinforcement material into the solvent, and then we are doing the ultrasonication, and then we will dry the powder to achieve the reinforcement in the powder form. So in that ultrasonication, this is the ultrasonication apparatus. In this ultrasonication apparatus, we are trying to break the agglomeration within the solvent material. So this is very popular for the specifically nanoparticles. This is the mechanical steering, same as like ultrasonication, but in spite of using ultrasonication apparatus, we are using the mechanical steering so that we can uniformly mix the two reinforcement particle. And another is the ball milling. This is the setup. You can see in ball milling, this is the jar. In this jar, there are some balls, and with the balls, we are pouring our reinforcement or matrix metal, whatever. Further, I will clarify this one. So, and then after this, we will ball mill this powder with the help of this ball. So we will get some uniform dispersion, but it has some implication also. So later we will discuss. Another magnetic steering, apart from the ball milling and ultrasonication, we are using magnetic steering to uniformly mix and dispersion of reinforcement particles. Apart from these two, this one is the low energy ball milling equipment available in our lab. It is not used for the dispersion, but it can be used to uniformly mix the reinforcement particle with the matrix or individual. So these are the dispersion technique mostly used. If you follow the composites research publication, you will get this easily. For fabrication route, earlier I told that the liquid state is very popular. In that liquid state, stir casting is more popular. So this is the schematic of stir casting. This is the schematic of squeeze casting. This is the schematic of ultrasonic assisted stir and squeeze casting. What we are doing in stir casting, we are casting the molten metal under the gravity. We are not using any secondary forces. But in the squeeze casting, we are casting the molten metal with the help of hydraulic ram to achieve the more dense specimen. So this is the squeeze casting. And in ultrasonic assisted squeeze casting, what we are doing, we are taking the help of ultrasonication transducer to get the uniform dispersion of reinforcement particle within the molten metal during the casting. So these are the very three familiar casting technique we are using. This is stir casting mold, which I can use for the fabrication. This is squeeze casting mold, which we have used for the fabrication of the specimen. This is very famous Ishikawa diagram to improve to get the better quality in MMCs with the stir casting, particular stir casting process. So what area you want to work, you can work for your PhD or whatever you want. In this slide, I want to highlight the most critical part. In stir casting, what is going on? This is the molten metal. Assume this is molten metal, and these black and white parts are the matrix material and reinforcement material. So while the stirring, what is going on? It will mix properly. But just after the removal of mechanical stirring, it will again sedimented. So what is the use of mechanical stirring? Because if just we will remove the stirring operation, it will sedimented. So we must remove this difficulty to achieve the better quality composites. So basically this is in molten metal. And what is the phenomena going on the ball milling? So as you can see here, this is the jar. In this jar, hybrid reinforcement powder is there and milling balls, but obvious. And if we ball mill the powder, so initially this is the 1 hour, like 30 minutes to 1 hour. What is going on? See, coating of the reinforcement particle in the matrix material or 1-2 reinforcement particle between this. It totally depends on what kind of reinforcement material you are using. After ball milling, okay, some agglomerates are breaking. Further, we can see that some agglomerates are very less in the 2-3 hour or 3-4 hour. What is going on in 4 to 6 hour? Okay, very less agglomerates. But another phenomena is coming what? Flattening. Flattening of reinforcing particle or destruction of morphology of the reinforcement or matrix material. So this is the major problem. So I went around 500 to 600 research article, and then I prepared this dispersion technique. Not very rigorously. We can use very small duration. We can vary the duration, and we can achieve the dispersion. Like here, this one is the reinforcement 1, disbursement 2, and we will mix in the acetone. Then we will perform the mechanical stirring. I mentioned the process parameter also, and we must follow the process parameter according to the reinforcement material. So I have mentioned in the range you can use for your materials. So we'll do the mechanical stirring, then we'll do the ultrasonication for shorter duration. 20 minutes is very adequate, but after 20 minutes, it will destroy the morphology or microstructure structure of the reinforcement. Then vacuum drying. We must dry our reinforcement metal in vacuum, otherwise it will oxidize. And then we have to do the ball milling for shorter duration to uniform mix, because one problem is there. If you do the ultrasonication, our powder usually in the wet form, not very dry. So first we need to ball mill, and then we have to again preheating of the reinforcement or hybrid reinforcement mixture before adding into the molten metal. So we will get very good reinforcement mixture. So based on the literature, I modified the whole stir casting process methodology. So first step, we need to follow the pre-dispersion of reinforcement. Then we need to do the stir casting process. This is the modern stir casting technique, which needs to be developed for fabricating very high strength composites. So I already got the patent in this design. In future, I will try to fabricate this machine also. This is the stir casting sample, and this is the squeeze casting sample. So from this setup, we can achieve the uniform dispersion of reinforcement. We will avoid the harsh agglomeration of nanoparticle, specifically nanoparticle, I am saying that. And to achieve the significant grain refinement, improve property of the resulting composites, and it can be used for both micro and nano size reinforcement. Apart from the stir casting, this is the conventional powder metallurgy processing. This is I'm highlighting the word conventional because most of the researchers are using this conventional powder metallurgy. First step, powder atomization by gas atomization or water atomization. gas atomization, we will achieve the spherical powder. In water atomization, not very spherical, but random kind of particles. So based on upon your application, like in our lab, people are working on the thermoelectrical property. So in thermoelectrical property, they are using the water atomizer, but we are doing the additive manufacturing. So specifically in additive manufacturing, we need the spherical powder. So we are doing the gas atomization. So there is a difference. Further, we will mix the reinforcement and matrix material through the ball milling. And after that, there is two kind of process. First is the compaction followed by the sintering. Second, compaction and sintering. So this is the conventional old fabrication methodology. This one is the modern, we can say that. And in these three, like hot isostatic, hot processing sintering, SPS is the most widely used. In lab, we are using SPS, and we found that this is very good processing technique. So based on the previous literature, I developed this schematic for modern powder metallurgy processing. First, like processing of powders, means through gas atomization, then dispersion technique, pre-dispersion technique, we can also say, then mixing of matrix material and reinforcement material by using this route, and then we can do the compaction and sintering in parallel way. So this powder metallurgy processing condition must be used to develop the composite with improved property, whatever the property, thermoelectric, thermomechanical or mechanical. I know this figure is not very well visible, so I published this image in my review article, so you can follow that also. Yesterday, Dr. Ajay Kumar highlighted the friction stir processing for fabrication of composite. So this is the normal friction stir processing for fabricating of composites. Step 1, machining of groove. We can produce the groove, and then we will fill this groove with the reinforcement, and then we will process the groove with the help of FSP tool, and then after FSP tool, processing of FSP tool, we will get the final composite. And these are the some FSP tool which we are using in the FSP. So after the reviewing the literature, I recommended this route for FSP processing, so we can get the very good properties in the resulting composites. So first, before filling the hybrid reinforcement in the group, we can pre-disperse the reinforcement, and then we can do the FSP with the recommended FSP process parameter. So we'll get composite with good properties. Another approach is the ARB process. This is the conventional ARB process which researchers are using now. So I have recommended this novel ARB process so that we can produce composite. Like first initial matrix material is strip kind of matrix material. Then we will do the annealing treatment for various duration. It's totally dependent on the what kind of material we are using. Then we will follow the anodizing and cutting metric strip into two halves and degreasing it to generate the grooves. And after generating of grooves, we will put the reinforcement material within the two matrix plate, and then after stacking, we will do the roller. We'll do the rolling operation with either in hot condition, either in roll condition. It's totally dependent upon the matrix and reinforcement material. Then we will get with very good ARB processed hybrid composite specimen. So apart from the conventional route, some additive manufacturing processing is also nowadays very popular. So with the help of additive manufacturing, we'll reduce the weight of the final specimen. So the capacity additive manufacturing have, so we can use it for a better components which can be used for aircraft or automobile field. So these are some MAM manufacturing, means metal additive manufacturing techniques like direct and indirect. So in this DD and PBF are more widely used among the researcher. This is the market trend by AM material. Like see from here you can see the metals are widely used in the additive manufacturing, and these are the some application like mobility and aerospace, medical and dental, defense and energy and resources. In this field, we are using the additive manufactured specimen in nowadays. So from literature review, I observed that among the other additive manufacturing technique, DD, SLM, and WAM are the widely used. In DD, what we are doing, we are depositing the powder layer by layer, following by the heating and the melting to get the final composite specimen. But in SLM, what is going on? Powder bed is already there. We will use the laser source to melt the powder and layer by layer deposition to form the composite specimen. So before processing DD and SLM, you can follow the reinforcement pre-processing to get the uniform dispersion of the reinforcement. Specifically in nanoparticle, because in like carbon nanotube or graphene particle is highly agglomerated. So you must use some ultrasonication or ball milling technique to de-agglomerate them. This is the WM process in which we are using the either matrix or reinforcement in the form of wires. So before using in WM, we must produce that wire, composite wire, to fabricate the composite. So as per my knowledge and my understanding of the literature, the DD is more used to fabricate the composite. In my recent review article, I mentioned that there are some SLM prepared composite, there are some DD processed composite. So number of composite prepared by the DD is more. So here I am focused on the DD. So based on the literature review, I recommended this novel ultrasonic assisted gas atomization process. So with this kind of novel ultrasonic assisted gas atomization process, we can prepare the composite powder. Nowadays, what we are doing, we are preparing the powder through the gas atomizer, but we can prepare the composite powder also by using this gas atomization process. What I have suggested, we can pour the molten metal with the help of ultrasonication transducer. So this ultrasonic transducer, what will happen? The nanoparticle agglomerate will break within this process, and we will get the very good composite powder with the uniform dispersion of reinforcement particle. So further, after the gas atomization process, which we can follow the reinforcement pre-processing route, and we will mix with this route the matrix material and reinforcement particle, and further we will do the DD processing. And DD processing, what I have recommended, there is one heater behind the substrate material, so we will maintain the melting temperature throughout the process. It's totally depend on the processing condition. I am not suggesting for every material, but you have to follow the literature for doing this fabrication. And while fabrication, we can use the ultrasonication transducer to uniformly disperse this reinforcement material within this powder melt. So this is the schematic of modern processing condition which we can use to fabricate composites. Now, high entropy alloy. There are so many reinforcement materials are available. We are using high entropy alloy material as a reinforcement also, matrix also. So you can observe this during the literature review. And this high entropy alloy can be fabricated by the casting also and powder metallurgy also. In our lab, we are producing this high entropy alloy by using the gas atomization. So we are getting very good property by using the gas atomization. Casting also, but while reviewing and while publishing, we observed that powder specimens are more popular and more good as compared to the casting specimen. So I wanted to tell you, that's why I told. So this is the conventional alloy. This one is the high entropy alloy. So what is the difference between them? This schematic is clearly showing. This high entropy alloy is the 5 to 35% volume percent of whole alloy. So this is the difference, and you can know, we know what is the entropy. Entropy is the disorderliness of molecules. Basically, we are teaching students like that. So what is the high entropy alloy? If we have one glass like this one, if we have one glass, in this glass, if we fill the reinforcement material, So it will close, it will fill up to the total volume. But if we fill the high entropy alloy, it will not agglomerate. Because why it will not agglomerate? Because it will have the high disorderness of molecules. So in that way, high entropy alloys are are more popular among the reinforcement, and we can use them in high temperature also. So there is one advantage also. So as we can see from this diagram, nowadays so many publications are available in the HEA composites, especially by additive manufacturing also, and it's now increasing. In 24 it is the most 258 on the additive manufactured HEA composites, and 4329 on the conventional manufactured. So there are two kind of alloys. One is traditional alloys, in which 1-2 principal elements are there. In second is high entropy alloy, in which at least 5 principal elements are there. So people who are working in high entropy alloy can relate this. The Cantara alloy is the five principal, having 5 principal element, and most widely used among the all HEA. And this is the cross-sectional view of the engine of the jet. So from this diagram, we can see that every part of the engine we are using the HEA, and we can use the HEA composite specimen also to improve the performance. Now fourth topic, and very critical topic of my FDP, material characterization. It is very important, and I want to highlight that some people are very new in this. Maybe they are attending this FDP apart from some doctorate, and they want to do PhD. So if you want to do PhD or explore your expertise in research field, so this characterization is very important. So what we are doing after fabrication, we are characterizing it with the help of either mechanical property investigation. So in mechanical property, tensile property, we are investigating like UTS and yield strength, then hardness, then compressive, flexural, elastic modulus, creep, fatigue, elongation, and impact energy. So these are the characterization which we are estimating for mechanical property. And further, microstructure analysis. Microstructure analysis to observe what is the available in the at the microstructure level within the composite or conventional alloy. So we can observe through SEM, TEM, FESEM, AFM, and laser scanning microscope, optical microscope, optical profilometry, and EDS and EBSD also. We can observe the microstructure. This is physical characterization. To somehow we can identify the phases, somehow we can identify the dispersion, stability. So these are the physical characterizations. It's totally depend upon if you are using the polymer matrix, you can go in the different way. If you are using a metal matrix, then you have to go for the XRD and not UV. UV is used for the polymer composite. So it depends upon the total what in which field you are working. Then this is the machinability, that turning, milling, drilling, erosion, ECM, and DCM. I will explain in further slide also. And this is the wear property investigation. There are two kinds of pin on this and ball on this. And people nowadays people are working on corrosion resistance also. So this properties also you can estimate. So for upcoming researcher or who they are very new participants, so that's why I kept this PPT in my presentation. This is the XRD machine, so you can familiar with the machine. This is the powder size analyzer, so you can analyze the powder size. This is the powder flow analyzer. After fabricating the powder through gas atomization or water atomization, you can analyze the powder flow through this machine. This is the powder classifier. If you want to classify the powder according to the size, like 15 micrometer, 100 micrometer, 150 micrometer, or in the range of 100 to 200 micrometer, so you can use this powder classifier. This is UV analysis. I use this machine for stability analysis of the dispersed solution. So you can use also this also. This is specific surface area measuring instrument, which we can measure the specific surface area of the powder. this is the optical, this is the microstructure analysis apparatus, and this one is the optical microscopy, followed by the polish. This is the polishing machine. Then we can observe the grain boundary within the prepared specimen. This is the SEM, and this is the FESEM. What is difference between the SEM and FESEM? I can show you in my PPT also. In SEM, we can analyze the specimen, but not very clear picture. So we must go for the FESEM. Why I am highlighting this? Because I went so many times to analyze my nanoparticle in SEM, but coming back with empty hands because I am not able to observe the nanoparticle. So I went through the FESEM, and in FESEM is very good. So you can use FESEM. This is the TEM. If you want to observe the micro level or very up to the atomic level, you can use the TEM also. This is the FIB. Before going into the TEM, you have to do the FIB. So in FIB means within the FESEM they will fix the specimen, and within the FESEM also they will analyze which part you want to analyze in the TEM, so they can fabricate. This is the FIB specimen. And this is the 3D FM. So we can use the surface profile of the specimens. Means we can analyze the surface profile of the specimen. This is the mechanical property analysis apparatus. This is the hardness, Brinell hardness. This is the Vickers micro hardness machine. This is the tensile. In this tensile machine, you can analyze the UTS, yield stress, UC stress also, and flexural stress also you can analyze in this specimen. But we need to change some mountings. This is the fatigue machine. This is the creep machine, and this is the nano indentator. Basically, nano indentator installed within the SEM. So while doing the SEM, you can do the nano indentation also to observe the hardness and elastic modulus. This is the machining analysis, CNC turning machine, which I used in my experiment. So I highlighted this also. This is the wear test machine. This is when a pin on disc, and this is the ball on disc. What is the difference between pin on disc and ball on disc? In this, pin is rotating and disc is stationary. In this one, disc is rotating and ball is stationary. So in this way, you can differentiate. This one is the surface roughness measurement. After the machining and wear test, you can analyze the surface roughness of the specimen to observe what is going on with the tool and the machined surface. This is the vibration analysis. If you are looking for the fabrication of structural component, so you can observe the vibration analysis also. So this is the honeycomb specimen we have fabricated to analyze the vibration properties of the prepared specimen. Sorry. So now comes to the what is my contribution to in this field. So I want to highlight most of my publication, but due to my lab constraint, because if paper is under publication or submission or under review process, so we can't show that data. But what are the work I already published? I'm highlighting through this PPT. So first work, we have prepared some high entropy alloy powder, aluminum Cantor this is, and this is the medium entropy alloy, Fe based medium entropy alloy. These two powders I prepared by the gas atomization process. You can see very spherical powders we prepared, and further we have performed the ball milling operation followed by the SPS. So from the SPS we can we will fabricate the bulk with the varying reinforcement percentage or varying proportion also. Whatever you want, you can play to fabricate your specimen. After that, we measure the density of the specimen. I am going fast because PPT is means this slide having more number of slides. That's why. So this is the density we have measured for the prepared specimen. This is the morphology of powder, very spherical morphology. This is the cross-sectional and EDS analysis of the prepared powder. This is the cross-sectional image analysis of the HEA, and this is the cross-sectional analysis of MEA. We can clearly observe the dendritic structure and their composition, means what is the going on within the dendritic structure. So further, we have observed the XRD. Whatever I presented in the previous slide, the techniques which we can used for the property estimation, I have used in our characterization. So this is the XRD which we have used to analyze the phases, what kind of phases available in our powder. So by using this kind of figure, you can say there is a deviation in the peak of the XRD. So there must be some property difference. This is the XRD of bulk. So you can highlight what kind of phases. Usually reviewer will ask from XRD what kind of phases you are observing in your specimen. So through your XRD, you can mention, you can highlight that. This is the sum of the prepared specimen. Here you can see the increasing proportion or decreasing proportion, and EDS also. From EDS also we can analyze the distribution of the various HE and ME. This is the EBSD analysis of the specimen. Usually we can observe the refinement in the grain structure, so that we can relate with the mechanical property. This is the mechanical property and YS comparison, yield strength comparison. So we must highlight our value reported and other researcher reported in the literature. So reviewer will be found some novelty. So yes, he is comparing his own result with the previous literature. So he will more interest in publication. This is the nano indentation analysis. This is the HEA specimen. This is the HEA surface. This is the MEA surface, and this is the means we can say the interface. So I have analyzed the nano indentation at HEA phase, MEA phase, and interface also, so that we can relate what is the trend of hardness. Like here, HEA, aluminum HEA, Cantor HEA is showing more hardness than FEMEA. So you can relate this kind of property. This is the sum of the deformed specimen and showing the microstructure. You can easily analyze what kind of deformation is going on, how much sample is deformed. You can analyze easily. And this is the TEM of the nowadays. If you want to look, if you want to publish your data in high impact factor journal, they are looking for the TEM. So you must do the TEM for your specimen. So in this TEM, we are analyzing what is going on the atomic level, where is the oxide, how much distribution of the oxide throughout the specimen, and then through this HRTEM we can analyze what is the other oxide particles are available. Like in this HEME interface, we have observed very novel kind of oxides which are not explored until today. So you can find this kind of means observation in TEM while using the TEM. So this is the schematic of showing the microstructure, deformed microstructure after 50% reduction, 90% reduction. You can show this kind of schematic. It is very good for the final schematic. Another research, we have fabricated the Cantor HEA with the magazine reinforcement particle by the SPS. So this is the this is the analysis of magazine nanoparticle by using the FESEM. See here, this is the FESEM image. In SEM, you can't observe anything. So you must go for the FESEM for the nanoparticle specifically. So this is the FESEM image of the magazine nanoparticle. Then we analyze the TEM to prove that yes, we have fabricated the magazine nanoparticle. Otherwise, reviewer will ask whether you have fabricated magazine that is belongs to magazine family or not. So we must follow that procedure. This is the SEM image of the HEA. So we can see the spherical morphology, dendritic structure. This is the cross-sectional image analysis. This is the powder image. And this is the EDS. So we can analyze the distribution of the allying elements throughout the. This is the morphology of 30-minute ball milling, Cantor magazine composites. So you can analyze what is the going on behind the ball milling to the powders. So here you can see the some non-destruction, means to not destructed spherical powders structure. Here is spherical, but here barely, very rare you can observe the spherical powder. So this kind of analysis you can do in your research. Then powder size analysis. After ball milling, we have performed the PSA, means powder size analysis, to how much is change in the powder size. So we can relate with the mechanical property also. This is the particle size difference for the different composite, different percentage of reinforcement. Then density measurement, how much densification we have achieved during the SPS. Then this is the XRD, how much other phases are present in our specimen. Then cross-sectional SEM-EDS of the powder to achieve the dendritic structure or powder morphology destruction. Then SEM-EDS of the bulk to observe the distribution of magazine reinforcement or other reinforcement within the composite specimen. And this is the micro hardness. So we are observing the increasing hardness with the improvement in the reinforcement particle. This is the engineering stress curve. In this, I want to highlight that nowadays, if you mix the reinforcement material, we will easily achieve the higher UTS, but ductility is reducing. So we must focus on the ductility also. If we improve the UTS, it means we can't say that we improve the mechanical property. Why? We lose the ductility. So we must focus on the ductility also. So as per my suggestion, if you are working, so you have to focus on the ductility as well as UTS both by using some novel reinforcement, novel pre-processing, or some secondary processing routes. So this is the EBSD of the prepared composite. You can easily observe the grain refinement. So reviewer will be happy. Yes, there is a grain refinement. So okay, Hall patch theory or some different extracting mechanism is involved in your processing or within the composites. This is the temp. We must highlight the dislocation pileup or reinforcement particle present in our specimen, and some nano deformance, tune or staking fault within the specimen, so that we can relate what is the reason behind the increment and decrement within the of the properties within the composites. So this kind of analysis we have to do for high impact factor publication. This is the wear rate estimation and tribological characteristics we have done. So according to the sliding duration, what is the wear rate pattern is going on, we have analyzed. We have analyzed the coefficient friction also, and wear depth of the wear track, so we can relate with the increasing of sliding duration or load, what is the going on the wear track of the specimen. Then to analyze the wear track surface, we have performed the SEM. Here we can observe what is the going on in the wear track. So you can use these techniques also. So here we observe the deformation, plugging, groups within the specimen. So we can analyze this and say in our publication, so that reviewer will be correlate this. And then we must observe the morphology of wear debris. Here we can see the fine debris, and here we can see the coarse debris. So we can relate what is the implication of these both in our specimen. So this is the last two publication belongs to this lab, and this now onwards this publication belongs to my PhD work or after PhD work. So this is another study. I have used ultrasonic assisted and steel casting and skids casting apparatus to produce the aluminum 6061 based composite and nano composite. Since my starting, I am very curious about the effect of various reinforcement. That's why I did this work. I have used SiC, boron nitride, TiO2, Al2O3, MWCNT, and graphene nanoparticles to prepare the composite. And I want to highlight that which composite is the best for researcher. So before fabricating, I have done the ultrasonication of CNT, and you can see that the agglomeration is decreasing as the sonication is going on. And this one is the ball milling of graphene. So as the ball milling is increasing, somewhat agglomeration is reducing, and some fine powder particles also you can observe. And this is the optical microscopy. So from this optical microscopy, you can observe the grain refinement within the composite. So here you can see that this is the grain, very fine grain structure specimen. This is the very fine grain. This is the some kind of very extremely fine grain. So you can relate with this grain refinement with the mechanical property as per the Hall patch deformation mechanism. So further, I have observed flexural, micro hardness, tensile, and hardness like Brinell. So we can relate what is the implication or what is the effect of reinforcement. So here you can see flexurical property is almost high in boron nitride and MWCNT, but micro hardness is very high in MWCNT, and again tensile stress is very high in BN and MWCNT, and hardness is very high in SiC, Al23 and graphene. So there is some deviation. Why there is some deviation? Always reviewer are asking. So we can relate that this SiC, Al23 and graphene are the ceramic particles. So these ceramic particles are responsible for improvement of the hardness, and this MWCNT tubular structure is responsible for improving the mechanical property, or BN nanoparticles are very promising to improve the mechanical strength of the resulting composite. So you can relate with your nanoparticle with the resulting properties. So these are the fracture. So we must analyze the fracture surface of the specimen. So what kind of fracture, where is the agglomeration, where is the empty pockets, where is the pores, where is the brittle fracture or ductile fracture, we can easily observe. Another research I have performed the dispersion of MWCNT for the different duration, and then stability analysis. For stability analysis, I have done the dispersion for 5 minutes, 15, 30, 45, and 60 minutes, and observe with the photographic images. Even I have performed 30 days also, means what is the going on after 30 days. So you can do this kind of investigation also. And why this TEM and EDS and XRD? Because sometime reviewer will ask, you purchase the material or you produce the material, so that belongs to produce material or not? Means if you claim that you are claiming that this is the MWCNT, but produce me the proof. So you have to attach the TEM or EDS or XRD to prove that yes, whatever you produce or purchased is belongs to that material. So this is the SEM. Yes, that time I told you what is the difference between the SEM and FESEM and TEM. So this is the SEM image of MWCNT. I observe nothing. I want to observe the agglomeration or dispersion of carbon nanotube, but here I am not able to observe any very good data. So I went for TEM. In this TEM image, you can observe that very clear microscopic images, and we can see that this is the 5 minute, this is the 6 hour. So very shortening, MWCNT shortening is there through sonication. Here through ball milling, very nanotube shortening. So there is a difference between the sonication and ball milling also, and you can clearly observe through the TEM because it is high magnification microscopic image. And further, if you want to do the HR TEM also, so is there any destruction in the morphology structure? So you can analyze this kind of microscopic images through nanoparticles also. So if you are analyzing nanoparticles, my suggestion, go for the TEM. So another research it is, in this I have performed the different fabrication route to fabricate the composite. So this is the route 1, this is the route 1. I have done the sonication for MWCNT and TiO2 separately. But in route 2, what I have done, I have mixed MWCNT and TiO2 into the one solvent, and then I perform the stirring and sonication to uniformly mix the MWCNT and TiO2 reinforcement particle. Further, I have observed the FESEM image. This one is the FESEM image. In previous image, like this one, we can't observe anything. But here FESEM is very clear. So this is the SEM and this is the FESEM. Here we can observe the coating of TiO2 particles over the MWCNT. Not very clear, but okay, we can say something from that image. So in another route I have followed, route 3. So first mixing, then stirring, then ultrasonication, then ball milling. So this is the microscopic image of the powders obtained from the route 3. So here we can observe very individual TiO2 particle for 6 hours. This is R3. So sorry, 1 hour, ball milling for 1 hour, and this is just for 6 hours. Very few TiO2 particle available in over the nanotube. So there is a difference between the ball milling duration also. So as per your literature review or research goal, you can do the dispersion process. So this is route 4, I already explained. And you must have measure the average particle size also for after the ball milling, so you can relate what is the going on behind the ball milling apparatus. And then you have to observe the XRD, is any other phases are available. So in my case there is no any other phases. This is the EDS of the MWCNT TiO2 nanoparticle mixture. So we can see the different SED index. We can claim that there is very kind of deformation, deflection because of ball milling. This one is the MWCNT and TiO2 interface. This is the MWCNT particle, and this one is the TiO2. So we can say that there is some dislocation or deformation within the particles. This casting methodology I have used, so you based on upon your reinforcement, you can use the casting methodology. In this methodology, what I have done 4 routes and then casting methodology with the ultrasonic assisted stir casting and skis casting. So I prepared both specimen. So this is the same EDS of the specimen. We can observe the dispersion of reinforcement particle within the specimen, and we can relate further. What is the agglomeration, how much is the agglomeration, in which sample we are observing the good uniform dispersion. So from this image we can observe. This is the optical microscopy, so we can observe the grain refinement also. Here in squeeze casting sample I have observed very less agglomeration and porosity. So I can say that this squeeze casting is very good approach to fabricate the MWCNT TiO2 aluminum 6061 metal metric aluminum. And in this specimen, I am getting the higher micro hardness also. So we can relate this this kind of structure property relationship. This one is the tensile stress strain curve of different specimen. As I highlighted earlier, this is the aluminum 6061. See here we can see the higher ductility, but this is the composite specimen. There is less ductility. Yes, UTS is increasing, no problem. But why ductility is decreasing? We must focus on that, so we can go for the high impact factor journals. Okay. So this is the FECM images. Vinod sir, I'm not watching the time, so if time is about to finish, just let me notify. So this one is the fracture analysis. Here we can see the TiO2 cluster, MW.
Sir, tell me, sir.
Yeah, yes, sir.
Do you ask anything, sir?
I'm not watching time. If time is about to finish, let me know, because
sure, sir. Still you have time, sir.
Yeah, okay.
5 years.
So, so from this FECM image, we can observe the MWCNT ropes also. That's why I said that FECM is more popular, more useful than the SEM image. So, if you are going for the nanoparticle, go for FECM. Here is the TiO2 cluster, MWCNT cluster, which are responsible for the ductility decrement. So we can relate this. Here also in another route also I have observed this kind of pores filled with the MWCNT TiO2 clusters. So I can say that this processing route is not good. Here there is a agglomeration, like kind of observation. So this is the another study I have performed. This is the machining investigation of the prepared composite. So first I prepared stir casted specimen, and then later I prepared squeeze casting specimen to observe the machining analysis. So this is the stir casting ultrasonic assisted mechanical steering stir and squeeze casting apparatus. We can produce the stir casted specimen also, squeeze casted specimen also. This is my processing methodology, and this is in my fabrication methodology. From this same image, I have analyzed the ball milled reinforcement particle mixture. So what is going on after the ball milling? So these are the high magnification same image. Here we can see the HBN and HBN particles are uniformly coated over the graphene nanoparticles. So we can relate this kind of, we can show this kind of morphology changes after the dispersion technique. Here we can see after the prolonged 6-hour ball milling of duration, nanoparticles are highly sticked in the graphene particle, and graphene particle also flattened due to intensified ball milling. And this one is the same image of SiC HBN nanoparticles. So here we can see the coating of HBN nanoparticle over the SiC particle with the increment in the ball milling duration. So here we can see the agglomeration destruction also and particle destruction also. This is the same EDS. EDS I have not attached because we have observed the SiC and HBN over the SiC, HBN over the SiC particles. So from here we can say that okay, very uniform dispersion and no agglomeration kind of behavior. This is the optical microscopy of squeeze casted specimen. See, this is the aluminium 6061, aluminium 7075 through the squeeze casting, no reinforcement. But here, this one is the HBN graphene, this one is the SiC HBN. So significant grain reduction, significant grain refinement. So we can say that as per Hatchpel theory, there is significant grain refinement. So mechanical property will increase like that. Here I observe the strength of the aluminium 7075 and hybrid composite specimen. So I observed that graphene HBN hybrid nanocomposite having more mechanical property as compared to other. And but in SiC composite, SiC HBN, I have observed more hardness because SiC particle is the ceramic particle, and ceramic particle are mostly used to improve the hardness and wear property. So we can cite the literature also, and we can claim our result also. So this is the fracture image of the specimen. Here we can see the HBN particles within some pores or some dimples. So we can say that these HBN particles are agglomerated or entrapped between the specimen. So that's why this hardness is increasing or ductility is reducing or UTS is increasing. We can interpret our data with highlighting this kind of fracture analysis. Further, I have analyzed the machinability analysis. So what is the going on behind the machining investigation? So I have done the machining condition under the dry condition and MQL condition. Machining under dry condition means tool is directly involved with the specimen. But if we machined under the MQL condition, means minimum quantity lubrication, means minimum quantity means very fine droplet of lubrication is impinging between the tool and the machine surface. So for preparing this MQL, we have used the HBN nanoparticles also, so that we can improve the efficiency of the working fluid also. So here we can see if we increase the feed rate, surface roughness is increasing. But if we are machining, this one is the aluminium 7075 specimen. This is the hybrid composite specimen. So in hybrid composite specimen, we are observing the less surface roughness. Why? Because that HBN particle or graphene particle are self-lubricating nanoparticles. If I use the SiC, it will increase the hardness, but it will complicate the machining operation. But if we use the graphene or HBN particle, it will increase the mechanical property, it will increase the hardness and reduce the machining characteristics also. So based upon this kind of literature review, we can use different reinforcement for varying the property also. So this is the picture of cutting tool we have used in our investigation. And this is the relationship between the surface roughness and feed rate. So what is the relationship between them? If we are increasing the cutting speed, then surface roughness is decreasing. If we are reducing like that, we can relate. This is a chip morphology specimen, analysis after the machining. This one is for the aluminium 7075. This one is for aluminium 705 graphene HBN hybrid nanocomposite, and this one is the SiC HBN. This one under the dry condition, this one under the MQL condition. So what is difference between them? See, Here very long entangled chips. Here, okay, not very long but entangled. If you relate here, very short length chip. Here, very short length and spring kind of morphology. So from here we can observe during the machining what kind of observation is going on, or what kind of phenomena is going on. So from this image, we can analyze that the self-lubricating hybrid nanocomposite, because of adding HBN and graphene, showing the low surface roughness as compared to the conventional composite. So which can so we can use this composite in the component where it will subjected into machining operation. Because composite preparation is another thing, application is the another thing. So for application, we must produce, we must surface finish our specimen. So for surface finishing, either we can use milling or turning. So within turning or milling, how our specimen is behaving, we must analyze. So this is the another investigation in which I have mixed graphene and Al2O3 reinforcement particle in aluminum 6061 based hybrid nanocomposite. This one is the flexural specimen. This one is the tensile specimen. Again, similar kind of apparatus, but with different process parameters. In previous slide, I mentioned as per the material, as per the reinforcement, we have to choose the process parameter. So you can get. This is the density. What is the trend is going on? If we use the different percentage of reinforcement, if we use the different processing technology, we can analyze with the density of the specimen. Then here optical microscopy. Here I have observed that graphene and Al2O3 hybrid composite specimen having the very high grain refinement. So it has some implication in the mechanical property also. This is the same image showing the flexural strength, means why it has very low flexural strength, why it has very high flexural strength. We can relate with this kind of property structure relationship. This is the weaker hardness properties. So 5 HNC showing the highest weaker hardness, but 2 HNC is showing the highest Rockwell hardness. Why? Because Rockwell hardness is the macroscopic and weaker is the microscopic. So if we are using more percentage of nanoparticles, means hard nanoparticles, so but obviously it will increase the micro hardness. But if we are using the micro size reinforcement particle, it will increase the micro hardness. So this kind of variation is also there as per the various reinforcement particle. This is the strength. So 2 HNC is showing the highest strength among the other compositions. Apart from metal specimen, I have investigated the carbon fiber and glass fiber hybrid composite specimen also. We have prepared the sandwich panel with the help of honeycomb structure. Here you can see the top layer is the carbon fiber, bottom layer is the carbon fiber. In between, we have fixed the aluminum honeycomb structure to analyze the vibration analysis and flexural analysis. So this route we followed for preparing the nanocomposite, hybrid nanocomposite. First, we mix the carbon nanotube in the solvent, then sonication for certain period, then heated the epoxy. We will mix the heated epoxy into the CNT solution, and then again sonication, because if we sonicate the CNT alone, it will behave different. If we mix the epoxy and CNT and then if we perform the sonication, it will behave different, because the epoxy is very gummy kind of liquid. So in gummy kind of liquid, CNT will fix and very rarely affected by the ultrasonication. So we must follow this process very carefully. Then this CNT plus epoxy solution we have poured in the carbon fiber, and then we perform the vacuum bagging to produce the CNT reinforced polymer fiber nanocomposite. Polymer is the epoxy, fiber is the carbon, and reinforcement is the CNT. So more than one reinforcement we can say. So this one is the flexural investigation of the prepared sandwich panel. Here we can see different behavior according to the reinforcement percentage. So this one is the specimen 2 showing the highest loading capability. This is the face sheet failure, means top and bottom layer is fabricated with the help of carbon fiber. So it got damaged during the flexible. So how it got damaged, why it got damaged, we need to analyze through the microscopic analysis. So this is a failure of honeycomb structure. So different specimens showing the different failure kind of mechanism. So we can analyze also. So I have performed diverse investigation. So I cannot conclude all study in a single PPT, but every study have different conclusion you can analyze in my publication. But general conclusion I can say that the nano reinforcement are most promising, but we have to uniformly disperse that nanoparticle within the composite specimen. So that is a major challenge we need to overcome. As compared to the conventional reinforcement, high entropy alloys are the populars, but we have to look for a proper composition, proper processing condition, so that we can play with the strength ductility balance. Okay. Then additive manufacturing technique, or the most most promising technique, but one article I have gone through that additive manufacturing is failed to delivered, but we can't say that because additive manufacturing is recently grown almost 10-15 years. So every new technology will take some time to deliver the real-time application or real-time product. So it is taking more time. So in future you can see the printing of whole rocket component or 3D printing of whole structure through the additive manufacturing technique. So we must focus on that particular processing condition or material. So it has some potential, but we need to spend some time. But obviously it will take more 10-15 years. Then more in-depth studies on the processing structure property. These three words itself is the PhD topic of your PhD topic. If you are doing the PhD, means if you follow some processing technique, so what is the implication of processing in the structure? Okay, then structure, what is the implication of that structure into property? So you have to analyze these three words in your materials. So this is the very important thing I have noted during the investigation. Then secondary processing technique are gaining increasing research attention. Yes, of course, because if we are mixing reinforcement into matrix material, UTS is increasing, but ductility is decreasing. But recently I have observed they achieved 1 GPa of titanium matrix material with the help of secondary processing, means heat treatment. So but obvious, so with the help of cryogenic processing, heat treatment, rolling, hot rolling, cold rolling, we can improve the property of the resulting specimen or composite. So we must focus on the secondary processing. It is costly, but we need to spend some time on that also. We have to put greater emphasis on the real world application rather than the high impact publication, because high impact publication will publish, if today I will publish one paper, okay, 10 days, 15 days, 1 year, 2 year, I will get 100 citation, 200 citation, but nothing matters. If you produce one component which can be used for the real-time application, that it has a very high impact. So rather than the publication, you can go for the real-time application. And future work should focus on the deeper insights like microstructure level. TEM is the compulsory, means every reviewer asking about the TEM if we are going above five impact factor publication. So we need to go for the deeper interpretation and concept. What is the concept behind that? Means we need to focus on the deformation mechanism, some strengthening mechanism. So many papers are investigation. What is the strengthening mechanism are involved in this mechanical structure property relationship. So we must focus on that also. After this, I would like to thank to participant and organizer for giving me this opportunity. I have started from very beginning because at one time I am also new, so I want this kind of information from FDF. So I put it from very basics. So I would like to end my presentation here. If you have any question,
Sir, I consolidated the questions in chat box for you. So
okay. 1 second, sir. Why is it important in material science? Why is it important? Means I didn't get the question.
Can I read, sir?
Yes, sure, sir.
Sir, why it is important? 1 minute, sir.
Oh, sir, what is important? Means which in which aspect you are asking?
Why it is important in material science? I don't know. Wow, I can't even.
Okay. sorry, Vinod, sir. Why, sir?
What are the common techniques used to analyze materials, and how do you choose the right one?
Okay, sir. If you are going for the microstructure analysis, if you want to observe the microstructure, so I highlighted so many times in my PPT. So if you want to go to the atomic level or very high magnification image, and if you are using the nanoparticles, you must analyze through the TEM or FSM. If you want to use only powder particles of the micro size, so you can go for the SEM. So based upon the particle size and particle behavior, you can use the techniques. If you want to analyze the mechanical property, so if you want to analyze the tensile, then go for the tensile testing. If you want to observe the creep, so go for the creep testing. So in that way, you can use the right one.
So next question is, how can material characterization help improve the performance of material in the real world applications?
Sure. Material characterization is very important, because if you fabricated the specimen and if you have not analyzed the property, then how you can claim that this material is most suitable for specifically automobile or aerospace. So if you are going for the automobile, like I have investigated wear analysis for my specimen, so I can claim that this material have more wear resistance, so we can use this material in a brake pad application. So if I observe, in last study I have presented carbon fiber, polymer, graphene or CNT hybrid nanocomposite, and I prepared the sandwich panel. So if it has the more strength, so we can say that this is sandwich panel which we can use in the automobile structure body also. If I investigated the aluminum 6061 or 7075, so I can say that this aluminum 6061 hybrid composite is mostly suitable for automobile frame. So with the achieved mechanical property, we can focus on the application. Yes. Next question.
What are the some challenges or limitation in current characterization methods?
Current characterization, like if we are claiming that our sample is the most suitable for the aircraft or aerospace application. So if I develop the nickel based or titanium based and we have done the mechanical characterization, So if that component is going into space, so there is a diverse range of temperature, like negative to positive. We are using that titanium and vanadium or nickel into the heat seed also. So we must analyze the property in the that state also. Like we have to analyze the mechanical property in the heated temperature scenario or heated atmosphere. So in that way we can say that this is the limitation, current limitation, because we are not heating the specimen. In some cases we are heating, very limited cases we are observing the thermomechanical, but we have to analyze that also based upon the application.
Uh, Dear participant, do you have some other questions? Means you can raise, unmute yourself and ask, or else you can post in the chat box itself. Dear participants, do you have any questions? Okay, sir. So we will conclude the session with a short thanking note to you, sir. Hello.
Yes, sir.
I think so. There is no question from audience, sir. So within short thanking note, we will conclude the session, sir.
Okay, sir.
So on behalf of the organizers and all the participants, I take this opportunity to sincerely thank our esteemed resource person, Dr. Sourabh Kumar Soni, sir, for delivering such an insightful and engaging session, sir. Surely today our participants and everyone will came to know about how the material characterization, what are the valuable things in that. So surely your expertise, valuable inputs and practical perspectives have enriched our understanding and made this session truly meaningful, sir. So really we are grateful for your time and effort and dedication for sharing your knowledge with us. So once again, I'm thanking you, sir.
Thank you, sir. Thank you for giving me this opportunity. I would like to know the feedback so that I can improve. Okay. Thank you, participants. So I'm
Thank
leaving,
you.
sir.
Okay, sir. Thank you, sir.
Thank you.
Dear participants, you are asked to stay in the meet itself. Next session will be started soon.